2.2 of Griffiths. So this is again a problem before we really get started in the meat of Griffiths, which next is the infinite square well, which just cannot be understated in its importance. If you learn nothing else from undergraduate quantum mechanics, or if you're not in physics and you want to learn something about quantum mechanics, it's going to be the infinite square well. So before we do that, we're doing a little bit of formalism. I already did problem 2.1. I'm going to be honest, I maybe didn't understand what he's asking for because I thought those were like really trivial. And perhaps I didn't quite understand what the point of them was. So it is incredibly possible, and by that I mean, yeah, I think I maybe trivialized the solutions because I didn't quite get what the point of the question was. I thought A was good. I just didn't get B or C. It just seemed like the same question. Okay. Now we're going to get to 2.2. This is also a very easy question, but I think it gives us a little bit more physical insight, and there's a little bit more to it, or at least there's more to it that I understand, so that I can explain it better, or that I can maybe have more fun with it because I understand what it's asking. Okay, so here we're going to start with our time-independent Schrodinger equation, and then he just rewrote it, so it's the same exact equation. All he did was just rewrite it for convenience. So del squared. I suppose I should be using full derivatives, actually. I realize I haven't been for literally no good reason, so I shall switch over to using full derivatives now, because there's only a variable of x. I mean, we specifically said that the wave function is only a variable in x, because we did separation of variables, so I really should do full derivatives. Okay, all you do here, multiply both sides by 2m, negative 2m over h bar squared. So I get d psi dx squared, negative 2m h bar v psi equals negative 2m over h bar squared e psi, and then we add this guy to both sides. I don't know why I'm going through justifying this, but it's the little stuff you forget. Just in case you're wondering, I will still always check units on something, even if it's something stupid like k in infinite square well, just to make sure my units are good. Okay. So that's all he did to get to this point, and perhaps this is beneficial to the people who aren't in an undergraduate physics class, which I just realized one of my goals was to make this more accessible to people who haven't done all the math, and here I am just blowing through all this without making very good justifications. So I'm sorry, and I'm going to try to do a little bit better. So let's go ahead and slow down for a second. We start off with this equation here. This is our time-independent Schrodinger, or actually I should say this equation here, my full derivatives time-independent Schrodinger, meaning that my little psi, my wave function, is a function of x and x alone. It is not dependent upon t. So, what this means is that the slope of this function psi in x, whatever it looks like, it can have whatever crazy shape it wants to have. Our wave functions are going to be determined such that the slope of the slope, right, is going to be determined by the potential and the energy. So if we have something like two atoms bonded together, you know, where the electron can sit is going to depend on the potential energy of this core and this core. That's going to limit the wave functions of a particle that can be in that potential, in that system. That'll also limit the energies that that particle can have. Now here, he just rearranged it a little bit, so I went through how to do that. And that's just so that we can get a little bit nicer picture of how these are related. So the second slope, the slope of my wave function with respect to x equals a constant multiplied by my potential energy minus my total energy. And my total energy is all the energies of my particle added together. So that's like my, we had it before, where we could write this in terms of my Hamiltonian operator acting on psi equals the energy levels times psi, or the total energy of psi. So E is my total energy, V is just my potential energy. And relating this back to Newton's law, F equals ma. Second derivative with respect to space is like my motion, my acceleration. Sorry, they're mowing the lawn outside. Alright, now let's look at what the question's actually asking. It is showing that show that the total energy must exceed the minimum value of the potential energy for every normalizable solution. And then ask you what's the classical analog. Okay, so our classical analog is going to be, let's say we have a ball, and let's say we have a hill, and its height h. And I come up to the ball, and I plan on kicking it because I'm having a bad day. So you kick the ball with some velocity v, and you want it to get up the hill h. Now the total energy of my system is going to be kinetic energy plus potential energy. Now typically kinetic energy, just so you know, is written as a T and potential energy is a V. I don't know why that became the thing. There we go. So we have kinetic energy and potential energy. You probably saw them written like this if you took high school stuff. Potential. Okay. So I have my total energy, or my Hamiltonian is my kinetic energy plus my kinetic plus potential. What this is saying is that my total energy is saying here, your total energy has to be bigger than V minimum. So if I want to get the ball up here, then my potential energy is just from gravity, that's mgh. In order to get it up that high, I need to have a kinetic energy that is bigger than mgh, meaning that my kinetic energy, 1/2 mv squared, must be bigger than mgh. So my guy has to kick it here with a velocity that is big enough to make this kinetic energy enough to go all the way up the hill. If it's too small, the ball will go up to here and then it will fall back down again. I need enough energy to get it over the potential and onto point X. So I have to have more kinetic energy in order to get that to work. So what that means in a classical example is that whatever number for my kinetic energy is bigger than my number for my potential energy. My total energy is something that is at least the size of V plus V. So my energy has to be bigger than the minimum. Even if I got it right up to the point where it's teetering up there, like just barely enough energy to say peek outside, I would still have to have kinetic energy at the very least be equal, meaning that my total energy would be equal to 2 times the potential energy. So that's our classical example. There are cases that we're gonna see later with, like say tunneling through a barrier. So classically, you know, that's what I got here for this guy. You have to kick the ball, it has to go up and over. Quantum mechanically, we will see that we could have something, you know, like say a photon and then it decaying through a barrier and then emerging out the other side for tunneling. We are not talking about tunneling here. We are talking about, because in tunneling, that's when we have something where, you know, we split it into psi 1, psi 2, and then we're going to have psi 3. In the region of psi 2, yes, we will have that the energy of the particle is smaller than the potential, but that's allowed because we have psi 1 and psi 3. Or at least we have psi 1. So for the case of tunneling, we always have the particle start outside the barrier and then go inside the barrier. This is talking about like a much more generalized case where we have, say, some energy landscape that looks like this, where we just have this constant V, and then we have a particle that has an energy level below that barrier over all space. So that's what we're talking about, just to differentiate here. Okay, why doesn't it work? Well, let's look here. We have dx equals to m h bar v minus e psi. Okay. Now, our solutions to this are going to be an exponential, and it has to be an exponential because the slope of my wave function is equal to my wave function times some constants. So if I just say that I have some constant c, let's just clean this up a bit. And my constant c is this whole chunk, right? And then if E is smaller than V, this is positive. So that means that the slope of my slope, the second derivative of my wave function with respect to space, has the same sign as just my wave function. So you can draw it out where if I have some wave function, I have an increasing, I could either have an increasing slope, and then the slope of that slope is increasing. Or I could have an exponential decay, but the slope of that slope is increasing as well. So whichever sign I have for my wave function, the slope of its slope has the same sign. So my solution can be psi equals, and we can have some constant a to be more exact here, just cx. So if I take the I'm actually going to leave out the c, because we can always just, constants don't matter, we can always just wrap them all up. In case there's anyone watching this who isn't particularly mathy, I know before you get into differential equations, like people who are really good at arithmetic don't really like this idea of just not caring about constants. So sorry about that. But nobody cares. Okay. If I take the derivative of that, d dx psi, that's just going to be that square root of c e to the square root of cx, and then I take the second derivative, so the derivative of the derivative, I get square root of c, square root of c, e to the square root of c. So we just get c, just that constant out that we already said what it is. Okay. I could also have a negative. I could also have a decay. So I could also say that psi is this guy, because then by the time I take the second derivative, the first derivative gave me square root, negative square root of c. My second derivative gave me another negative square root of c, and then I got that. Why isn't that normalizable if it's a negative? Well, because we're talking about normalizing over all space, which is that pesky negative infinity to infinity. And this function, let's just say, there we go. We'll keep the square root. There we go. Now this one, we could say plus or minus. There we go. We work out this guy. We get plus or minus that. And then we have plus or minus this thing, evaluated at negative infinity to positive infinity. Now the negative solution so for the decay, it diverges there. So I get e to the positive infinity, and e blows up. So for my exponential decay, I have a diverging factor when I go to negative infinity. For my positive, I have a divergence at positive infinity. So this is not normalizable over all space. That's kind of the thing there. Yes, for tunneling, we will get an energy that is below the energy of the barrier. So that's one of the things that is like not allowed in classical mechanics, that is allowed in quantum mechanics, but that can't exist over all space. So that's where we get the issue there. Tunneling is supposing that we had a particle start in a place where its energy was above the barrier. Here it is just not normalizable over all space. And that's how we show that, because the exponential function is either going to diverge at positive infinity or it's going to diverge at negative infinity. And there you go. It's because they have the same sign. That is the key. And there we go. That's 2.2. So again, not hard. It's a pretty easy one. But it's a lot of, this is more, these 2.1 and 2.2 were about putting the physics into the math. The stuff that we're talking about, like more of these mathy proofs, that's going to come in chapter 3. So next time we're going to do infinite square well, and I cannot understate the importance of infinite square wells. If you learn only one thing from quantum mechanics, learn infinite square wells. Preferably learn more, but if you're that kind of person that really is determined to only learn one thing, I mean, I don't understand that. Probably you'd be determined to learn 0 things. But anyway, if you're going to limit it to one, do infinite square wells.